Welcome everybody. If you want, you can put your name in the chat. Thank you for coming this week. And hello to everybody who said I in the chat. Just make sure that you put your name in again, because if you put it in before I started recording, then you're not going to be recorded for attendance. So you need to type your name one more time. Okay. Okay, I hope everybody had a good week and is getting ready for a good weekend. Today, we're going to do a transition in the course. So we'll go over the one homework problem, which is a statistics problem, and we'll go over the one problem, which is a statistics problem. But then we're going to start to do a little overview of geometry, which is going to be what we do for the rest of the fall and the winter. So today we're going to be just giving kind of an overview of plane geometry, of two-dimensional geometry, and we'll start getting into more specific things in the next session. But just to start off, I want to just go back over this homework exercise that we had about this mean and standard deviation of the group data. So we have a table over here with with 5 different groups for our data. So the amount of time it takes for something to happen. And then we have a frequency table. So that says the number of measurements that are in each of this range. And what we want to do is, as best we can, is to calculate the mean and the standard deviation of this group data. And now, again, because it's group data, you're never going to get a precise answer. You're just going to get, as good an approximation as you possibly can, okay? Because the data is not precise. You don't know whether these 123 measurements, maybe they're all close to 10, maybe they're all close to 20. You don't know that, and so the best that you can do is more or less assume that they cluster around the midpoint of each class range, and that's going to be good enough to get you what you want. Okay. So so there's a formula for the standard deviation over here, but maybe let's maybe not look at that yet, because the first thing that we have to do is calculate the mean. Of the group data. So does anybody want to show how we can calculate the mean of this group data from a frequency table here? What calculation we have to do?
I think hello?
Yeah, Princeton?
Yeah, I think to calculate the mean, you have to
Gabriel, sorry.
All the frequency and divide by the total number of that is given.
Right. So we have all the frequencies, right? But what do we have to multiply each frequency by in order to get the mean?
We need to find the midpoint.
The midpoint, right? So we have midpoints for all of these ranges, which I'll just write down. The midpoint here is 5, 15, 25, 35, and 45, right? So as Princeton, as Gabriel were saying, you have to use you have to multiply the midpoints by the frequencies, right? So we have here 5 times 37 plus 15 times 123 plus 25 times 350 plus 35 times 116 plus 45 times 40. And then what do we divide by?
The total number that is given.
The total number that's given, exactly. So 37 plus 123 plus 350 plus 116 and plus 40. And I don't know if anybody has done this already. I can try to do it.
Dr. Abdus?
Yeah.
Hello, Dr. Abdus?
Yes, Ed?
Hello?
Ed? Yes.
I think it would be still preferable. Let's draw another column and then put a class midpoint. They'll put all these values, they'll multiply,
sure.
they'll get it.
Sure, okay, that makes sense.
Easier for us.
Okay, great.
Okay.
So we'll do class midpoint. Okay, that's a good idea. So class midpoint here is going to be 5, 15, 25, 35, and 45. Okay, so that's going to be the class midpoint. Great. Sorry, remember, if you're not answering or asking a question, please mute yourself. Okay, so great. Has anybody done this calculation already? And if not, I'll just do it. So 5 times 37 plus 15 times 123 plus 25 times 50. Yeah. Hello, yes?
Hello.
Yes.
I did solve the problem, but at least you together the only.
Mm-hmm. So what did you get as your results?
But I put in a group chat.
Oh, okay. It's in the group chat. Oh, wait, I don't look at the group chat while I teach. So, oh, you have it on paper that you sent to the group chat a while ago, right? Okay, so let me see if I can find that. I have to open my WhatsApp, which I'm not usually checking while I'm teaching because it's too many different things to look at. So do you have your answer on you?
Yeah, the answers are there.
Okay.
When I did it,
right.
I think I seen it. Yeah, when I did it, some of the frequency. You getting me?
Yeah, I can hear you. I'm opening my WhatsApp now because I need to open up the program to see the group chat. I'm not looking at it right now, but.
Yeah, I sent it on November 11 by 6:14.
Okay. Right. So it's 166, 11. Sorry, my WhatsApp is loading. And here we are. Okay. Let me just see this. Okay, here we are. I'm looking for, all right, I see this. Okay, so somehow I'm getting, yeah, 16,640 and 666. Okay, yes, I see what you have right there. So 160, 510, 626, yeah, 666, great. Okay, and so this comes out to be 24.985, looking at what you had there. So 24.985, that's great. So this is correct, and this is the mean. Okay, so before we move on to the standard deviation, which I see that you also did, is there?
It is. Hello.
Yes, Gabriel.
Yeah. So I use other formula that I told you about.
Oh, okay. The other formula. So you have the sum of the
fx squared.
Oh, I see. Yeah. So you're doing the sum of fx squared divided by n and then divided by the mean squared. Okay. Yeah. I think that this formula should be equivalent to the one that I've done. So let's so you got, this will be a good exercise. So you got 9.06 using this other formula. So let's do it with my formula and we should get the same answer.
Sure.
So let's try them both, okay? But before we do that, any questions from anybody else about how we did the mean here?
Yes, Dr. Ross?
Yes, Princeton.
Yeah, concerning the class midpoint.
Yeah.
I have a doubt there where we just start with 5, 15, 25, 35, 45. I don't know how it came about. Please, can you elaborate that?
Okay, well, the midpoint is just the average of the minimum and the maximum of your class. So this class ranges from 0 to 10. And so the midpoint is just going to be, for instance, it's going to be 0 plus 10 divided by, so if we're doing this midpoint, 0 plus 10 divided by 2, which is equal to 5. That's how you get the midpoint of each individual class.
Oh, okay.
And then you do that for each row. So 10 plus 20 divided by 2 will give you 15. It's giving you what's exactly halfway between the bottom and the top.
Okay, I understand.
Okay, great. Other questions? Okay, so let's do the standard deviation of group data. So Gabriel has a different formula which should be equivalent and should work, but let me just recall the formula that we did last week. So if we're given group data, we calculate the mean of the data, which we already have, and then we have the midpoint already, and we have the frequency of the ith class. And then we have this total number of measurements, which we found to be 666. So the standard deviation can now be calculated using the following formula. And what this is the sum over all the classes of Fi, which is the frequency, times the difference between that class value and the mean value squared. And then once you've taken that sum, then you divide the whole thing by n and take the square root. Okay, so let's add, as for Ed's suggestion, let's add another column to the table for this xi minus x bar squared, right? So I think we have space, actually. Just to make a little space, I'm going to delete this over here. So I'm going to add maybe 2 more columns to the table. So this one, so this class midpoint, which is what we call xi. So then here, what we're going to have is we're going to have x minus xi. And then here, we're going to have fi times x minus xi squared. So in this case, the midpoint, what we're looking at is the difference between 5 and 24.985, right? So over here, we're going to have, I guess we're taking the, sorry, this should be the mean. So we're taking the mean and subtracting the class midpoint. So this is going to give us 19.985. This will give us 9.985. This will give us, right, so this will give us, we're subtract, so this is negative 0.015 when you subtract to this minus 25. And then each other thing is 10 more. So minus 10.015 and minus 20.015. Okay. And so now over here, we have these new frequencies, these new frequencies to calculate. So let me see what they are. So these new frequencies are, I'm just going to have to do them out with a calculator. So we have 37 times 19.985 squared, which is going to be here. This is, I'll just round to whole numbers. So 14,778. And then I have for the next thing, 123 times 9.985 squared. That's going to be 122,663. Then I have 350 times minus 0.015 squared. That's going to be essentially 0. Comes out to more or less nothing. Then I have 116 times negative 10.015 squared. That's going to be 11635. And then lastly, I have 40 times 20.015 squared, and that's going to give me 16024. Okay. So when we add them all up, so the standard deviation from the formula, it's the square root of the sum of everything in this column. So that's 14778 plus 12263 plus 0 plus 11635 plus 16024, all divided by the total number of measurements, which we already calculated is 666, right? This is our n right here, is 666. That's the total number of measurements in the frequency table. And let's see what happens when we do this. It's the square root of 14778 plus 12263 plus 11635 plus 16024. All of this divided by 666. Let me see that. And I get 9.06, exactly what Gabriel got. So that is very good. So this comes out to be 9.06. Okay. And let me omit all. I'll box that in red. Okay, so the mean, yeah, so this is the mean, and this is the standard deviation. And one thing to keep in mind is you should do a bit of a reality check. Remember that the standard deviation is supposed to represent roughly on average, how far are your measurements away from the mean? So if the mean here is about 25, then our measurements here, sometimes they're 20 away, sometimes they're 10 away, sometimes they're very close, sometimes they're 10 away, and sometimes they're 20 away. So that this average, in some sense, is 9, is a very reasonable answer to get. If you got that your answer was 100 or something like that, or something negative, then you would want to look at this data and say, the answer could not possibly be 100. There is no sense in which this data is on average 100 away from the mean of 25. So it's always good to look at your answer and make sure that it actually looks reasonable. Okay, I'll try to be louder. Try to you know, to look at the answer and make sure that it actually looks reasonable. It's a good check that your computation is correct. All right, I'll try to speak right into the speaker. I can't find my headphones right now, which usually have the speaker. Actually, let me try these. Let's see. Let me see if these work. Let me try this. Is this any better for sound? Better, worse, the same? Does it make any difference? Better. Okay, good. Okay, so I'll wear the headphones then. All right, welcome everybody who just came in. It's good to have so many people here. All right, so any questions about this statistics question? And then I will mention Gabriel's method also. Okay, let me add just an extra page. So this is an alternative formula for the standard deviation. Okay, so what you can do instead is take the derivative, that's not the derivative. Yeah, both steps are correct. Sorry. So what you can do instead is take the sum over all I of fi xi squared, and then just divide that by n. And then you can subtract off the mean squared. Okay, I believe this is what Gabriel used with this in his formula. Let me make sure I'm getting this right.
Yeah, that's it.
That's it, right?
That's it.
Okay, great.
Yeah.
So this formula also works. This is equivalent to our other formula. Okay, and sometimes this formula can be a little bit easier to calculate because you don't have to calculate these differences. So it has an advantage. So an advantage is that it's easier to calculate with. Okay, it's easier to calculate with. And one, so if you're trying to do a problem and just figure this out, then that advantage is all that matters. You calculate with it, it's easier, and that's great. I'll say one disadvantage is that the meaning is not as clear. And what I mean is that, what is the meaning of standard deviation? Right? The meaning of standard deviation is you're trying to understand this quantity. How far away is your data entry from the mean? And what is that on average? So what's nice about this is that this difference between the data entry and the mean appears explicitly in this formula. So, I mean, even with all of these other ornaments, the square root, the dividing by n, what you can see is that you're still calculating something based on the distance from the midpoint of each of your class groups to the mean of all of your data. And you can see that if this quantity gets bigger, then your standard deviation will get bigger also. So you kind of, this formula allows you to see the meaning of standard deviation a little bit better. It's trying to tell you something about how big these quantities xi minus x bar are. But of course, it gives you exactly the same answer as if you use this formula instead. And this formula instead, I would say, yeah, I guess it's a little bit easier to calculate with because you don't have to calculate, sorry, this should be mean of x, not mean of xi. Mean of x squared. So with this formula, you don't have to calculate the difference between each of the midpoints and the overall mean. So, you know, to some extent, you have an advantage there. Okay, but either one is great and either one is correct, and it's good to know both. Okay, any further questions on this? Okay. All right, so let's start our new unit on geometry. So we'll only talk maybe 30 minutes about geometry today. We'll get more into formulas and problems next week, but I want to just say a little bit about what we're going to be doing in geometry, okay? So we're going to be studying what's called plane geometry, which means geometry in 2 dimensions. And so plane geometry is the study of geometry in the flat 2-dimensional plane. So like drawing on a piece of paper, what we usually do, standard geometry. And then the main quantities that we measure in this plane geometry are angles, lengths, and areas. And so let me just say that there are, you know, other kinds of geometry, which maybe if we want to, we can talk about a little bit later, although it won't be this semester. So other kinds of geometry. Sorry, please keep your mute on unless you're talking or asking a question. Okay, wait. Okay, so there's other kinds of geometry. So the main one is what's called solid geometry. So this is 3-dimensional geometry. About cubes and spheres and things like this. Okay. Sorry, please don't unmute yourself. Alex, you're becoming unmuted a lot. Please keep yourself on mute. Okay, unless you're asking or answering a question. Okay, so we have solid geometry. Then there's all other kinds of geometry. There's something called spherical geometry. There's something called hyperbolic geometry. And maybe if we'll have one day where we talk about all of this stuff. But let me just say very briefly what it is. So spherical geometry means that I have a sphere and I'm doing geometry, you know, on the surface of the sphere. So instead of drawing shapes in the plane, like if I'm drawing a triangle might be drawn like on a sphere like that. So things are going to be a little bit different. Hyperbolic geometry is geometry kind of like on the surface of, you know, something what's called a negatively curved surface. So something like that, where you have hyperbolic triangles that might look, you know, something like this. And you have all sorts of weird things that happen in spherical and hyperbolic geometry. So in this case, you know, the angles of a triangle add to more than 180 degrees. And in hyperbolic geometry, the angles of a triangle add to less than 180 degrees. And it turns out that these kinds of geometries can be very important, like spherical geometry. You need to do this if you're trying to do like large-scale navigation on the Earth or astronomy or things like this, because the Earth is more or less a sphere. And you can't really, if you're looking over short areas on the Earth, you can basically make believe it's a plane, and that's not going to matter. But there are times if you're looking at long distances, then you have to take into account the curvature of the Earth. So spherical geometry is not just some game that mathematicians make up, but it's really something that, is applicable to various, trying to understand, plane flight. How should a plane fly from one place to another? What's the best way to go? You need to understand that. You're talking very long distances there. You need to understand that on the surface of a sphere and not just in the plane. But for this semester, we're going to talk about plane geometry. Again, this semester, we're trying to stick pretty closely to the Liberian high school math curriculum. So we are going to stick with plane geometry now, but maybe we'll have a session or two about these other kind of interesting geometries later on. I will say there's even more weird stuff. There's something called projective geometry. And like the list goes on and on. I mean, you can even do higher dimensional geometry. Etc. Loads of different kinds of geometry, but the main things are plane geometry, and then to a small extent in high school, also solid geometry. So maybe we'll talk about that a little bit later on. Okay, so these are the things that we measure. Let me just briefly talk about each of these things. So angles, remember, an angle is formed by two rays or line segments originating from the same point. So if I draw an angle like this is an angle. And we measure, usually I draw a little curve here, and we measure, and for an angle, we often use the Greek letter theta when we're talking about the measure of an angle. We sometimes use alpha, sometimes we use regular Roman letters also. And the two main measurements we have for angles are degrees or radians. So remember, degrees are defined by, a full circle is 360 degrees, and then angles are measured based on what fraction of a circle they cover. Right, so for instance, if I draw a circle, and I have an angle over here in the center of the circle, let's say it's made by this. And so if this is, 1/6 of the circle, the angle measures 60 degrees. Okay, because if a full circle is 360 degrees, this is just by definition. Then for 1/6 of a circle, we would have 1/6 of 360 degrees, and that's that. Okay, so this is how degrees work. Radians are a little bit more complicated. I mean, they're very important when you're doing trigonometry. For most of our geometry unit, we're just going to be using degrees, but just to be complete, let me at least mention radians. So radians are an angle that cuts out an arc of a circle with length equal to the circle's radius is 1 radian. Okay, so let me, it's an acute angle, right? This is also an acute angle. Angles can be acute and obtuse and right, and I'll talk about that a little bit more later. So an angle that cuts out an arc of a circle with length equal to the circle's radius is by definition 1 radian. So let me just draw a picture of that on another page. If I have a circle that has radius r, this circle has radius r, and then if I draw this other angle, of course, every radius has length r, And if the arc length here is also r, so if the arc length here is also r, then the angle, if this is my angle theta, so then theta equals 1 radian. And it turns out, so in fact, 1 radian is equal to 180 divided by pi degrees, and which is roughly, I think it's 57 degrees. Let's see, 180 divided by pi. Yeah, so this is roughly 57.3 degrees. Okay. Okay. So it turns out that radians are very important in trigonometry, and really they're very important in calculus. That's kind of why radians matter. In order to make certain, derivative formulas in calculus work out, you really need to be working in radians. But for us, when we're doing standard plane geometry, we're usually going to work in degrees. Okay, so this is nice, if this angle, the way I've drawn this almost looks like an equilateral triangle, right? And you may know that an equilateral triangle has 60-degree angles. So it makes sense that a radian is something pretty close to 60 degrees, right? The only difference is that the arc length here gets a little bit longer than what the length of the line would be between these 2 points. So if the angle was actually 60 degrees, then connecting these 2 points would give you an equilateral triangle, which would be length r, but the arc length would be a little bit longer. So what that's showing you is that an angle that's 60 degrees is going to be a little bit more than a radian, because the arc length here is going to be more than r. But it's pretty close. So, I mean, a radian, actually, it turns out it's just a little bit less than 60 degrees. Okay. So this is kind of, an extra topic, but for us, we're generally going to be measuring things in degrees. And I should say also, just going back, that if you read Euclid, if you look at the original geometry proofs from Euclid, if you look at Euclid's Elements, then he does everything in terms of right angles. So we know that a right angle is 90 degrees. It's a quarter of a circle, right? But when Euclid talks about angles, he won't say 180 degrees. He'll say 2 right angles. So everything is measured in terms of right angles. So instead of 180 degrees, he'll say 2 right angles. Instead of 45 degrees, he'll say half a right angle. For an acute angle, he'll say something that is less than a right angle. And for an obtuse angle, he'll say something that's more than a right angle. So Euclid's reference point for angles is always a right angle. He doesn't talk about degrees and he doesn't talk about radians. He only talks about right angles. So you can do that. You can just take the right angle as your unit of measurement. The right angle is 90 degrees, and anything else is done in terms of right angles. So for example, over here, if we have a straight angle, so let me just say, so example, straight angle. So what does a straight angle mean? It just means that we have the 2 rays go out at a straight line in opposite directions, and we look at this angle. Well, of course, this angle is half a circle, right? So half a circle. So it's 180 degrees. It's also, if I draw this up here, it's clear that a straight line is 2 right angles, right? So we could say in Euclid's language, it's 2 right angles. That's what he would call a 180-degree angle. And then in the language of radians, we know that 1 radian is 180 over pi degrees. So if we needed to convert this to radians, we would have, so for radians, we would say 180 degrees times, so 1 radian over 180 over pi degrees. And so that's going to be 180 divided by 180 over pi radians. I'm sorry, I'm running out of space. I'll have to do this back up here. And when you simplify this, this comes out to be pi radians. Okay. So when you have an angle, you can think of it in these three different systems. It can be 180 degrees. It can be two right angles, the way Euclid would say, or it can be pi radians. Okay, so all of these represent the same angle, but usually we will talk in degrees. Okay, so any questions about angles? Okay, so let's move on. So we also talk about lengths. There's not that much to say about length. The length of a line segment is the distance from one endpoint to another. So, I mean, everybody knows what a length is. We have a line segment with two endpoints. The length is just the distance. In real-world applications of geometry, of course, we measure lengths in whatever unit of measurement you need to use. So we would use feet or meters or miles or light years if we're talking about astronomy, you know, whatever kind of length you want. But in pure mathematical study of plane geometry, we usually do not include units when we talk about lengths. We just say the length is 5 and we have some unit in mind. We just mean 5 units. Okay, so there's not that much to say about lengths of straight lines. Okay. Oh, let me take a look at the radian. Okay. Lengths of curved lines are not as easy a thing. So we'll have a day that we talk about circles and we'll talk about how pi figures into those lengths. In general, if you have curves and you want to understand their lengths, you really have to use calculus to do that. There's no way around that. But for lengths of straight lines, it's a pretty straightforward thing. Okay. James, are you okay? Can I move away from the page? Okay, all right. Well, in any case, okay, I'm gonna move on. Okay. So areas are an interesting thing. So areas are kind of, we have an intuitive sense of what area is, right? It should be kind of how much space a region in the plane takes up, right? And so at least for a rectangle, this is a very straightforward thing, right? We define the area of a rectangle to be equal to its length times its width. So if I draw a rectangle, right, rectangle with 4 right angles, then it has a length L and a width W. And of course, over here, this is also L and this is also W. And then the area is going to be equal to length times width. This is very straightforward. And then it turns out that if you have other figures that are bounded by straight lines, you can usually figure out these areas just by using one simple fact. And the simple fact is that if you have 2 figures that are non-overlapping, then the area of the total figure is the sum of the areas of the 2 individual figures. So for instance, if we had, let's do we'll do a parallelogram, but let me first do a right triangle. So why do we know that the area of a triangle is 1/2 base times height? Well, at least for a right triangle, if I draw a right triangle, meaning a triangle with 1 right angle, well, I know that I can go like this and have the same triangle over here, right? And so what we have is that both, so if this is, let's call this, well, I'll call this base and I'll call this height. If I add another copy of the triangle together, it makes up a rectangle. And so we know is that the rectangle, the rectangle with area base times height is made up of 2 non-overlapping right triangles. So each one must have area 1/2 base times height, because the 2 of them together make up the rectangle, which has area base times height. Each of the 2 right triangles, which are congruent, You can get one by flipping it around and superimposing it on the other one. That means they each have to have area 1/2 base times height. And if you're looking at figures with straight lines, basically every area computation you could possibly do comes from this principle. It comes from the principle a rectangle has its area formula, and everything else you can get by breaking it up into pieces and relating those pieces to rectangles. So we're going to do later on, we're going to do the area of a pentagon and a hexagon and in general an n-sided polygon. And all of this will end up going back to rectangles and going back to triangles. And what I'll say is that areas of figures that are not bounded by straight lines, so for instance, a circle or an ellipse or anything like that, figures or a heart or something like that with curvy sides, you basically have to use calculus to compute them. There are kind of ways around this, but even the area of a circle, pi r squared, that's not at all a straightforward computation. I can give you an argument that will maybe convince you that the area of a circle is pi r squared, but really the only way to actually prove this is to use calculus. So we're mostly going to be talking about straight line figures, so we're not going to have to use calculus. When we talk about circles, I'll give an argument for why the area of a circle should be pi r squared. But more or less, it's very hard to do this without calculus. And if you want to try to calculate the area of an ellipse or any other kind of curved figure, cardioid or something like that, you're just not going to be able to do it without calculus. Okay. So let's do one other example. So let's say we want to talk about the area of a parallelogram. This we do not need calculus for because it has straight sides. So let me add on another page. So example, area of a parallelogram. So let me draw a parallelogram like this. Let me do a better job drawing it. Let me try to draw it with straight lines. I think I have something that will make me, let's try that. Okay, that's pretty good. That's a better parallelogram. Okay, so, and let me call this, I'm going to call this side B, and I'm going to call the height here H. Okay, and so you may know that the area of a parallelogram has the formula base times height. Well, why does that work? Well, we know that the parallelogram, we can cut this little triangle piece off over here. I'm drawing a perpendicular line from the corner up to the top. Okay, this is a right angle over here. So I'm drawing this line up to the top. And then what can I do? I can put the same triangle over here, right? I'll just draw it shaded a little bit lighter. So I can put that same triangle over here. And then I create a rectangle. So the area of the rectangle is what? It equals the area of the parallelogram, well, minus this part of the parallelogram that I'm taking away to make the rectangle. Let me just outline the rectangle in another color. Let me outline it in green so that we see what rectangle I'm talking about. Right, this is the rectangle. So the area of the rectangle, which I'll box in green so you know what I'm talking about, is the area of the parallelogram, which I'll box in blue here. And then we have plus the area of the triangle, which I'll box in red, right? So it's the area of the parallelogram plus the area of this triangle, but minus the area of this triangle, right? I take the parallelogram, I add on this triangle, and I take off this triangle. So it's the area of the parallelogram plus the area of the triangle on the left, which I'll box in red, And then we have minus the area of the triangle on the right. And so area of the triangle on the left and the area of the triangle on the right. And altogether, this is just equal. So if I have the area of the parallelogram plus the area of the triangle on the left minus the area of the triangle on the right, well, these are the same. These triangles have the same area. So what we get is that the area of the rectangle is in fact equal to the area of the parallelogram. Okay. So keep in mind, I'm not doing a rigorous proof here. A rigorous proof, I would have to prove that these two triangles are congruent to each other, and I would have to prove that the areas are equal. And you can do geometry very rigorously, and maybe we'll do that at some point. But for now, I'm just trying to give like an intuition for why should the area of a parallelogram be the same as the area of this rectangle. At some point, we'll be a little more careful with our proofs. So the area of the parallelogram equals the area of the rectangle. That is its base times height. Okay, so this is the kind of proof that the area of a parallelogram is base times height. The point is you have a parallelogram. If you cut off a triangle and replace it over here, you haven't changed the area because all you did was move stuff around, but you do now have a rectangle, and you know what the area of a rectangle is. So just like we did with a triangle, here with a parallelogram, we've related its area to the area of a rectangle, right? And ultimately, all area formulas come from rectangles. All right, any questions on this?
Hello? You got me? This is Emmanuel. Hello?
Okay, so let me talk about various approaches to geometry. So there's kind of two main approaches to plane geometry. And the first one is what's sometimes called the synthetic approach. This is the approach of Euclid. This
Hello?
is the ancient approach with Euclid and the elements, and this is also all of the Greek mathematicians, Pythagoras, Apollonius, right? They're all using this approach. And then there's a more modern approach called the analytic approach, which comes from Descartes. So this is much more recent. This is from the 17th century. And this is the idea of doing geometry by working with coordinates, right? Euclid did not use coordinates. So let me just elaborate a little bit on these two different approaches. So the synthetic approach is that you start with some terms that you just take to be self-evident. So you take things called points, and you have something called a line, and you have a notion of what it means between. So what it means for a point to be between two other points. And maybe another notion, what it means to intersect, what it means that two lines intersect at a point, things like this. You have to have some basic notions over here. And then you have some basic axioms that you take for your geometry. So these are statements that you're just going to say are true from the beginning without any justification. But they're generally axioms that we take to be true because we experience them in our real life. And we say, well, if we're going to ultimately, if the goal of geometry is to tell us about space, tell us about where we live, then if we see things that obviously are true, then we're just going to take them as axioms. This is the only kind of thing that we want to discuss. So for instance, an axiom would be something like, for any two distinct points in the plane, there exists exactly one line passing through both of them, right? It's just saying that, every 2 points of the plane, they have a line, okay? And it turns out that if you have the right set of axioms, and Euclid had a set of axioms, turns out Euclid's set's actually not quite the right set.
Hello?
There are a few gaps there. It took until the early 1900s
Are
for
you
someone
getting me?
named David Hilbert to really correct this. But if you have the right set of axioms, or sometimes they're called postulates, that's basically the same thing, then you can work from the ground up and you can prove all of the statements about plane geometry from these axioms and from these definitions. And even though you're not really defining point and line in between, it's still useful to draw diagrams to aid in one's understanding. So when you do these kinds of proofs, you're usually going to be drawing lines, you're going to be drawing angles, you're going to be drawing triangles. And Euclid's Elements has lots of diagrams in it. So this is Euclid's approach to geometry, is you start with points and lines and some very basic notions and some very, very basic axioms, like there exists a unique line between 2 points. And then you go and you prove everything from that. So from that, you can prove that the angles of a triangle add up to 180 degrees. You can prove all sorts of theorems about circles and things about alternate interior angles and congruent triangles. And all of this stuff comes from these very basic axioms. Okay, so this is the approach of Euclid's Elements. By the way, one thing that it took people a while to realize is that this axiom is great for plane geometry, but this axiom is maybe no good for spherical geometry. So in spherical geometry, let's just look at the Earth. Let's just say I draw the Earth. It's the equator. And here's the North Pole. And here's the South Pole. Well, how do I draw a line from the North Pole to the South Pole? Well, when I'm on the surface of the Earth, I'm not drawing a line through the Earth's core. I have to draw a line on the surface of the Earth. So how would I go straight from the North Pole to the South Pole? Well, there's actually a lot of ways. I could traverse any line of longitude that I want to, right? So this is a line from the North Pole to the South Pole, and this is a line from the North Pole to the South Pole, and this is a line from the North Pole to the South Pole. And all of these will be experienced as walking along a straight line, right? You're just going on a straight line of longitude from the North Pole to the South Pole here. So in spherical geometry, this axiom does not hold. Here's 2 points on the Earth, and there isn't just one line between them. There's lots of lines. I can go on any line of longitude I want. So what I'll just say here, in spherical geometry, the axiom above does not hold. Okay, so the modern perspective on this is that we say that this axiom, it's not, well, right, I mean, notice that I wrote in the plane. So in the plane, this is a good foundation for geometry, because if you have 2 points in the plane, there is one straight line between the two of them. But on a sphere, this is not a good axiom because it doesn't hold. Okay, so what this means is that the kinds of theorems that you're going to be proving in Euclidean geometry are going to be valid in the plane. They might not be valid on a sphere, right? It may not be the case that the angles of a triangle add up to 180 degrees or whatever. Okay, so this is the synthetic approach in Euclid's Elements. Okay, let me say a little bit about the analytic approach. So in the analytic approach, we think of geometry, plane geometry at least, as taking place in the coordinate plane. So we give coordinates to all of the points that we're looking at. And this can often simplify proofs, although sometimes maybe coordinate proofs, people view them as less elegant, since the proofs tend to use a little bit more algebra and a little bit less geometry. So one of a statement that you prove in Euclidean geometry is the 3 medians of a triangle all meet at a point. Okay, and recall that a median is a line segment that links a vertex of a triangle to the midpoint of the opposite side. Let me actually not say a line segment, just because they could meet outside. Let me just say a line. Just a picture, right? If I have a triangle like this, then the median is I connect one side of the triangle to the midpoint of the other side. Here I take one side of the triangle to the midpoint of the other side. And here I take one side of the triangle to the midpoint of the other side. And a theorem in plane geometry is that all 3 of these lines are going to meet at one point. Okay, question for James. Can we divide the branches into the 2 approaches? I mean, usually people use a mix of one approach and the other approach, right? I mean, of course, classically, there were no coordinates. I like to use coordinates, but sometimes I do something for the other approach. So they do bleed into each other. But you can kind of do everything one way or do everything the other way. So this is kind of a picture of this theorem that the medians of a triangle all meet at one point in the center. This point in the center is sometimes called the centroid of the triangle. And well, so what do you have? How would you do an analytic proof? Well, then analytic proof would be, well, I'm going to give the vertices, the triangle lives in the plane, so I'm going to give the vertices names. Let's say one is at the point AB, one is at the point CD, and one is at the point EF. And then you could say, well, if I know what these 3 points are, then I can calculate the midpoints of the sides, and then I can calculate the equations of the lines that go from the vertex to the midpoint. And if I have all these 3 equations, I can calculate that there's going to be some point where they all intersect. Okay, that would be the analytic proof. And it's an ugly proof. Okay, you're going to have a bunch of ugly equations for lines, and you're going to end up getting some solution to all 3 equations. And if you've got a solution to all 3 equations, then that's telling you the lines meet in a point. But this proof, even if it's maybe a little more straightforward, it's a kind of proof that I think many people would say provides no insight. Okay, so you can prove that these medians all meet at a point, but the proof itself might not really provide you into any insight as to why that should be true. Whereas a synthetic proof would, that's a typo, would rely on drawing extra lines and using theorems about parallel lines and similar triangles and things like this. And even though this proof might be a little trickier, a little harder to memorize, it might also give you a little bit more insight into what's going on, why the medians of a triangle should all meet together at a point. Okay, so you have these 2 different approaches, and they each have their own advantages and their own disadvantages. Okay, so what did I want to say? Yeah, so in general, our emphasis this semester is not going to be on proofs. We're not going to be doing a lot of statement reason proofs where we draw diagrams and talk about alternate interior angles and show that things are congruent to each other. If there is demand for a semester where we focus on proofs in Euclidean geometry, I can definitely do that in the spring if that's what people want, but I'm not going to do that this semester, and I'll get feedback at the end of the semester and see if that's what people want to do next semester or if they'd rather do something else. Instead, what I want to do is focus more on formulas and their derivations, which I think is a little bit more relevant for the curriculum and for your students on WAS and whatever other exams they have to take. So we're going to focus on formulas for computing areas and lengths and angles for all sorts of different polygons. So we'll derive the area formula for a regular polygon, so not necessarily a triangle or a square. So if you have like a hexagon with a certain side length, what's its area, things like that. Okay, and we'll also talk about circles and various theorems that we have with circles. Okay, so that's going to be what we'll do for the next 2 months, basically, in this course. And yeah, so just one homework exercise. So this is going to be from the analytic perspective, not the synthetic perspective. So let's say that a triangle has vertices at, let me just draw this. So a triangle has vertices at 0, 0, 4, 0, and 2, 6. So 0, 0, this is 4, 0, this is 0, 0, and this is 2, 6. And the exercise is, first of all, to compute the equations for the 3 medians of this triangle. So each median is a line, right? It's a line that goes from one vertex to the midpoint of the other side. So I want you to compute the equations for each of these lines. So the lines will be like y equals mx plus b. There'll be equations involving y and x. And then solving these equations simultaneously, you'll be able to compute what is the point where the medians intersect. Now, of course, if you may know that there's a theorem that they intersect each other in a ratio 2 to 1, et cetera, we'll talk about this more next week. But what I want to just show is that you don't need to know any geometry. You don't need to know any theorems. One of the great things about analytic geometry is that it converts all of geometry into algebra. So if you can do algebra, then you can do geometry, right? And this proof right here is going to be a completely algebraic proof. You're going to find that these 3 medians meet at a point, and you're going to calculate the point, and everything will be done with algebra. We'll see next time how you would do a synthetic proof of this, meaning one that does not assume coordinates and that just uses kind of results from geometry. And that's what we're going to do next time. We're going to talk a little bit more about triangles. So logistics announcement, no class next week. It's Thanksgiving here in the US, so I won't be around. So no class next week. The week after, we're going to talk more specifically about triangles in some more depth. Okay.
Okay.
So
No problem.
and please remember, if you haven't yet put your name into the chat, to please do so before I end the recording. I'll say, so for James's comments, so the coordinates are all positive, but special attention should be given to 0. Kind of one of the good things about coordinate geometry and analytic proofs is that it doesn't really matter whether your coordinates are positive or negative. In the end, if you want to show that like the 3 medians of a triangle meet at a point, then that will work no matter what your coordinates are. It won't matter if some of them are negative, some of your points are in different quadrants. The proof that for instance, the medians all meet at a point will not give you any problems, no matter what kinds of coordinates you have. Okay. And so, sorry, when I'm saying to put your name into the chat, I mean the Zoom chat, not the WhatsApp chat. Okay.
Okay.
So to just type it in the Zoom chat, because that's what I look at to get the attendance list. Okay.
I'm
All right. So thank you all for coming. Thank you for your attention. And I'm looking forward to seeing you in a couple of weeks to do some more geometry. All right. Any questions?
Thank you.
Sange?
Yeah.
I think you're on mute. Not getting you at all.
I said thank you. Oh.
Hello?
Hello?
Okay. All right. Well, Emmanuel, we got you. We got you for attendance. Okay. Sange, did you want to say anything?
Hello.
Hello, yes. Marcus?
Yeah, Dr. Andrews, thank you so much for always giving us new idea. Yeah, especially the group data where we have a couple of steps, especially calculating the mean deviation analysis and that of standard deviation.
Mhm.
It's actually good every day, and this idea, if mathematics is all about practice, because sometimes you have to compare and contrast some questions that what we are doing here. Sometimes you look at the steps you practice, most of the time you get acquainted with those steps. So there are several steps that if you follow, you also derive at this standard deviation and other formulas you will find within this problem. Like even in group data, they have where you have to calculate the midpoint and the accommodated frequency and all of it. They are all in on group data and so on. So thank you so much. I always appreciate your effort.
All right, you're most welcome.
Thank you, sir.
Yeah.
Hello.
Hello, yes. Emmanuel? Hello? Hello?
Yeah, are you getting me?
Yeah, I'm getting you now. Emmanuel?
Okay. Yeah, I want you to please throw a little light on the syntactic proof of the triangle. I think I missed track a little. Can you please?
Oh, well, I didn't do it. I didn't do
you
it.
didn't do it?
No, I didn't do it.
Okay.
Yeah.
Okay.
No, I didn't do it. I'll
Okay.
do it next time. Yeah.
Okay. I thought
Yeah.
I was
No,
missing
that's why you
track.
missed it, because I didn't do it. Yeah.
Okay.
Yeah.
No problem.
Yeah.
So hello, are you getting me?
Yes. Yeah, I'm getting you.
Yeah, you were talking about plane geometry.
Yeah.
You talk about the steady, you talk about the mean quantity.
Mm-hmm.
And I want you to throw a little light on when you are discussing plane in relation to angle, in relation to angle.
Mm-hmm. So
You getting me?
yeah, I'm getting you. So maybe I want to make sure I understand the question. So I mean, we're going to prove things about angles and talk about, what is the sum of the angles in a regular polygon, all of these types of things. But I mean, for now, all that I really did was just define an angle. And for any angle, if I have an angle like this, which is the vertex, I can always draw a circle that has this vertex at the center, right? And so I can draw a circle around here that has this vertex at the center. And we just measure, all that I really said about angles is that we measure the angle based on what fraction of the circle it cuts out, right? Okay. So the whole circle is 360 degrees. And if it cuts out part of a circle, you just take that fraction of the 360 degrees, right? So if it cuts out 1/6 of a circle, like in this picture, then the angle is 1/6 of 360 degrees. So that would be 60 degrees, right? In plane geometry, your angles are formed by straight lines lying in the plane, right? The only difference is in these other kinds of geometries, in spherical or hyperbolic geometry, that the concept of a straight line is not as straightforward. So straight lines, even if it's straight on the surface, it's still going to be curved because the surface is curved. So and that's why these things are more complicated. But for plane geometry, you're always just forming it with straight lines. And so you can just draw a circle, and that's how you can measure the angle, by what part of the circle it cuts out. So I don't know, is this, I'm not sure I'm answering your question. Am I?
Thank you, Dr.
Okay. You're welcome.
Okay.
Okay, other questions?
Asking a question about this last.
All right, hello. Anybody else?
Yeah, hello.
Hello, yes.
You getting me?
Yep, getting you. Mm-hmm.
Yeah, okay. What could be the difference between the method you solve finding the standard deviation by invoking the midpoint and other element? Let's go back. Can you please go back to the slide, sir?
Yeah, so this standard deviation slide?
Yeah. Yeah, the one with the chart.
Oh, okay, here.
The one you have the chart.
This one.
Very good. Very good. Okay, so you have the time, the frequency, and the class midpoint. The means minus the x1. So what's the difference if I'm using the frequency, the value of x, the sum of x, and the sum of x squared? I try to do a chart using few of them. I get little different numbers, but at the end of the journey, I have 9.1.
Okay, if you have 9.1, you probably got it right. It's just you probably just rounded your numbers differently. Gabriel, were you going to say something? Yeah, so you will have a different chart if you're using the other method, which is this alternative formula. You would use fi xi squared. The numbers in the intermediate steps will all be completely different. But in the end, you should get the same answer. And 9.1 is the same answer as 9.06. It's just a question of how you rounded it.
Okay.
Yeah, so that's totally fine. You'll have completely different intermediate steps, but in the end, you'll get the same answer. Maybe not right now. A later time, I can prove that both formulas give you the same answer. Doing that proof is not that hard. Yeah, so 9.1 is fine. That's the same answer.
Thank
You're welcome. Other questions? Okay, so I will stop the recording then.